It's really a pleasure to be here. I think this is the 5th year running, and it's one of the things that's so fun about this workshop is you, no matter where you're coming from, you learn by being here much more than you ever teach, and so it's really a privilege. So today what I'm going to jump into is a general kind of framework for conducting a particular type of analysis in social networks, which is analyses that are trying to treat a higher level network measure as the dependent variable. And so the way we often think about this problem, which is the micro-macro problem in sociology, is that this is kind of a famous figure adapted for network language based on something that James Coleman drew many years ago, which we often call Coleman's boat, sometimes slightly derogatorily Coleman's bathtub. And the idea is that we have a macro level input and a macro level outcome that's measured at something higher than the level where individuals are actually interacting. And we can represent the association between the two, the macro and the macro, and we can represent the association between the macro and the micro. But getting back up from the interpersonal interactions or the granular things that are happening at the micro level to model a change at the macro level actually ends up being very, very difficult. And so what I'm going to be talking about today is kind of a statistical framework that tries to grapple with these problems. And what the framework is really doing is taking a number of simulation approaches that have been widely used for many years and repositioning those simulation practices, many of which have been kind of informal, within a potential outcomes framework. And once we make that small move, we're actually able to treat many of these types of things that have previously been thought of as agent-based models or computer simulations as target quantities that we can statistically estimate, derive the properties of, and understand to use for null hypothesis testing. And so these are kind of the key papers. Some of them are still in progress, some are under review. The main statistical R package I'll be talking about. I do want to direct your attention to something very subtle that you might not be able to read here, and that is the word Lewis. He's right there. And he's made some very important contributions to this software package and the development of these tools. He's a first-year grad student, and I hope you are watching what he produces. So, an overview of what I'll be talking about today. There's some key things to be aware of in terms of understanding this framework, which I'll call the micro effect on macro structure framework, or for shorthand, the MEMS. And the idea here is that the main characteristics that we're looking at is that a focal network structure is the dependent variable. And so to build intuition on this, Jim was talking earlier about how we have this range of models for modeling networks as the dependent variable. Things like stochastic actor-oriented models, which David will be talking about shortly. Things like ergom, things like latent space models. And a thing that they have in common is that when you're interpreting the coefficients, it tends to be something along the lines of the log odds of realizing a tie is forming as opposed to not being observed. This is a very helpful interpretation that gives us a lot of statistical traction. But many of you, if you're interested in how we draw social support from our connections, you might want an interpretation that simply, is this increasing or decreasing the number of connections I have? It's the effect on degree, not necessarily the effect on the log odds. So this is a minor kind of shift in how we're thinking about it, but it bears on a more general problem. We might want a function of the network structure to be our dependent variable. We might not want to model why we are seeing a whole network. We want to understand, is the fact that I'm befriending my friend's friends actually making this network more segregated? I want to explain why a specific feature emerges. And that's the type of move we're trying to make here. The second characteristic of the framework is that it's statistical. And so Carter Butts is going to be talking quite a lot on Friday about generative in silico simulation experiments, where we can take a generative model and simulate a whole range of other outcomes to varying input conditions and parameter values. Now, these frameworks are actually a little bit more flexible than what I'm going to be telling you about. But the advantage of the framework that I'm introducing is that we can think of it in terms of statistical methods. And so we can conduct hypothesis testing on the types of relationships we want to observe, and we can refute null hypotheses, as well as do some more complicated forms of statistical inference that I'll be talking about later. It's a post-estimation framework, meaning it's actually agnostic to the type of model you provide and the type of data structure you're using. So it can be a cross-sectional network, it can be a directed network, it can be a bipartite network, it can be a multi-level network, it can be a relational event sequence, a longitudinal network, a weighted network. Whatever you can think of and model in a statistical network framework, you can use within this method. The fourth thing that's important to know about it is the types of inference we can draw are bound to the cases. And so I'm going to come back to this a little bit later because we can interpret the values that we estimate as effects we observe in the observed data, but our ability to generalize to new cases is a little bit more tenuous using these frameworks. So, what types of research questions can we address? Well, there's a few that I try to come up with. Admittedly, I'm not a health scholar, so I was trying my best to think of health-related questions here. If these sound weird, well, I just told on myself, that's why. But some ideas such as, does dating through friendship networks concentrate sexually transmitted diseases in local network clusters? Does our preference to befriend members of the same racial groups create structural holes in organizational networks? Does the fact that I tend to help my neighbors actually contribute to pathogen hotspots in village household networks? The key feature in all of these is that this dependent variable is something about the clustering, the brokerage, or the structural holes, or the segregation that we're actually observing in health behaviors, or anything about the network, really. So in terms of what I'm going to go through first, I'm hoping to spend about 10-15 minutes on just defining, interpretation, and estimating the micro effect on macrostructure so we can get a handle on what it is. Then we're going to switch to R and talk a little bit about the software that you can use to implement it, which is very flexible software. And then we're going to come back and talk a little bit about more advanced kind of statistical inference tools using the MEMS, including sensitivity testing for some of the things Jim was mentioning earlier, as well as other threats to inference, and then more complicated analyses involving moderating variables and indirect pathways. So before we get into it, the thing that's really important to know about this framework is that the language of micro and macro is being used slightly differently than what we often think of in terms of just general vernacular. So in this framework, a micro-level process is anything that's happening at the dyadic level. And so we're looking at something that is driving two nodes to be connected. And it can be basically anything operating at that level, but it has to be a selection process. And so we can get something that's kind of maybe a little unintuitive to think about. But the idea is that you can have an effect like gender, which we have this well-known finding that girls in high schools tend to have more connections than boys. We can think about this as a dyadic selection process because it's driving connections to be formed towards girls at a greater rate than boys. Our outcome variable is anything we can calculate on the network structure that's above the dyadic level. So it can be a node-level attribute like degree centrality, betweenness centrality, the local clustering coefficient, reachability. It could be a subgroup measure, such as what is the average number of triangles within a cohesive community or a clique. It can be a global network measure, such as a measure of segregation, global transitivity, network density. If you can calculate it on the network, you can pretty much treat it as a dependent variable. So the basic problem that we're trying to look at here is we have some network that we want to observe. But the problem is that the feature we want to explain is a function of the measured data. So we have tons of different ways we could conceivably model this network that we're actually observing. We could plug it into something non-parametric, like a quadratic assignment regression. We could plug it into something like an ergom, which was the use case I often will be talking about. But at the end of the day, what we're trying to do is represent what's generating the specific network feature we're looking at, and then test why those relationships exist. So the general idea that's going into this is we can take some type of generative model, which we're going to represent with this very, very, very general functional form, F. And F just stands in for any model that you might pick. It might be an ergom, it might be a stochastic actor-oriented model, anything like that. Now, the thing that we want to test, the selection mechanism that we are theorizing about or have some idea about generating the macro structure, is going to be denoted by X. And so in a simple case, we might be asking something like, let's say Y is the level of segregation in a network, and X is the amount of preference individuals have for making friendships with members of the same racial group. Then the micro effect on macro structure we're trying to get is the amount that X contributes to Y. How much individual tendencies to create friendships with members of the same racial group drive up racial segregation. Of course, the problem we have is that there's a number of confounding processes that could be exacerbating or even interacting with the process we want. It could be the case that triadic closure in networks that are already segregated is exacerbating these dynamics. And so we're going to represent the alternative confounding mechanisms that we might want to control for or condition on with Z. So far, we're still in the standard statistical modeling framework. We have a model, we have a number of coefficients, we have our input variables that we're trying to interpret the coefficients for. And the key thing to note is that the coefficients here are the effects determining whether two people are more or less likely to be connected. So we have not yet gotten to this outcome variable we want yet. This is where the magic move happens, okay? Everybody ready for this? Pop. Okay, this is really debatably the most important slide. We're making a small kind of equivalence here where we're essentially saying y is a function, it's some feature of the network we're measuring. So we can express the outcome we want to look at, segregation between a centrality degree, as a function of that network. And since that network is a function of this model, we can further extend to say y is some type of function of those input variables and the associated parameter weights that we're exploring. Okay? So now all we've done is re-express this outcome we want to look at, the macro feature, y, as a function of this assumed input model. With me so far? Based on this, we're going to define essentially two potential outcome conditions. And this is where we're drawing our kind of statistical inference from. One is the potential outcome that we observe. This is the network that was on the slide before. It's featured in the observed data. We're assuming that we have our model specification correct, and we're representing our macro outcome as a function of that model. But the counterfactual we're comparing to is what that value of the macro outcome would be, or in other words, what that network would look like if we eliminated that selection process we're interested in. So this little toy example was developed with political segregation in mind. So consider this a network representing the level of political segregation that we observe in a small group. And let's say X is representing something like choice-based homophily, individuals' preferences to befriend other people who share their political views. This is the amount of segregation we see, and this is the network that we would expect if we eliminated people's preferences to befriend others with the same political views. So this counterfactual value is representing what we would expect the network to be if that key variable we want to study is totally eliminated. Once we do this, we can express our target quantity in pretty simple forms. The micro effect on macro structure is simply the change in that outcome value between these two potential states of the network. The one we observe in the data and the one that could exist if the thing we were interested in had no effect whatsoever. Okay? So far, what we've done is we've actually just re-expressed a very common type of in silico experiment. This is often called the knockout method in the published literature. The idea being you can take some model, some generative model, and selectively eliminate certain parameters and see how an aggregate structure changes. But since we formalized it, now we're able to start interpreting this as a target quantity and move it into a statistical estimation framework. So there's some things that we need to know about this particular estimand. The first is it's rooted in but-for causal logic. And so what I mean by this is the way we typically think about target quantities is in terms of what would happen to the data if I were to change the value of an explanatory variable across multiple conditions. Now, in the case of network data, basically everything is interacting with everything else. And so these functions are essentially the effect that we observe from our explanatory variable x is partly contingent on the values we have already observed for all other variables. And what this means is even though we can interpret the MEMS as essentially the total contribution of the variable we are interested in to the outcome we're interested in, we cannot necessarily say that it will generalize to new cases. Okay? So essentially what we can say is if we estimate a particular MEMS, let's say it's 0.15 for a political choice homophily effect on a political segregation outcome, we could say that the amount of political choice homophily increases the amount of political segregation we see in the observed network by 0.15. In other words, individuals' tendencies to befriend others who have the same political views increases the political segregation we see by about 0.15. Okay? We'll walk through an example in a moment when I get into some R code. The second thing to keep in mind here is that because this is case specific, the counterfactuals we're generating actually don't have a clear interpretation. Now, in some cases they might, but the big difference you'll notice here, and this is deliberate, is that we've just changed a lot of the ties in these data. And so sometimes what might be the case, a particular argument that comes up when we're looking at social networks, is imagine a counterfactual world where I truly enter a network where there is no possibility for me to befriend my friends of friends. I cannot access triadic closure. I know nobody. I have no mutual affiliates. Do I simply have less friends, or do I change my standards? Now, oftentimes people change their standards. And there's been studies on this, including David left the room, that David has done, looking at people entering new settings. And frequently, what they prefer in terms of the connections they make differs as they enter new networks with few structural characteristics to aid them, and then ingrain into those networks and have structural opportunities. So with this in mind, the really important thing to know about the interpretation is even with the MEMS, we can interpret it as the effect of a micro-level treatment on a macro-level outcome, but we cannot necessarily draw inference on what this counterfactual value means. So what we could not say in this prior example is that if political choice homophily were to disappear, political segregation would decrease by 0.15. You see the difference? It's the contribution to the data we observe, not what could happen in the absence of treatment. I saw your hand. Tell me a little bit more. Yep.
And you intentionally get those, and then you remove, I guess, explore what are some of the reasons why they are still mixing in ways that aren't, other groups are not. And then you kind of remove certain variables, and then you're like, aha, that's how we get people to come together.
Yeah, no, this is great. So I want to follow up on two things here. So one is that when we're talking about this counterfactual isn't interpretable, what I mean is as long as it is truly counterfactual in the sense something we can't observe, we can't interpret it. But your point is exactly right. What if we can sample a network which, all else equal, has all the exact same properties of this network, it just has no triads? Actually, yeah. Now all of a sudden we don't have the same type of counterfactual problem. We still have some issues with the types of assumptions that go into this about the comparability of the networks, but that gets us closer. The second thing I want to say is when I say this counterfactual isn't interpretable, I partly mean it under the assumption of specific contexts. So, for example, in the context of drug markets, we often think about the dark web drug market as being a place where people with severe dependencies go. That's usually not the case. People go on if they have severe dependencies, they already have a distribution channel. Oftentimes, people go on the darknet because they are college kids who want to experiment with LSD and have just found access. Now, you're that person. Well, you're probably not, but we once were, right? And at that point in time, we enter the dark web and we think we have two counterfactual worlds. One where I have a lot of information about vendors' past distribution practices, and one where I don't. Do I buy the drug if I have no information? Now, this is a very different setting than the case of social networks. We don't necessarily draw social support from our drug distributors in the same way we do from our friends. And so what this implies is that in some cases, this counterfactual might actually be reasonable. It might be the case, for example, could eBay have succeeded if there was no star rating system? Most prior studies say probably not. The reputational information that was provided by electronic rating systems on online markets is really essential for their success. Otherwise, you're just throwing money to a stranger and hoping it works out, right? And so this counterfactual in some cases might be reasonable, but it has to depend on the substantive knowledge. And that goes to the follow-up I want to say, which is when I say this counterfactual isn't interpretable, it means I have not derived the formal properties to interpret it yet. I have derived the formal properties to interpret this side. So not interpretable based on current knowledge, not necessarily never interpretable. I hope that makes sense. Other questions for clarification, because we need to understand what the MEMS is before we keep going into more of the routine about it. We're good?
What happens if the microfactor just means like the absence of ties?
Say again?
Like what happens if like the
allowing for connectivity. But that doesn't necessarily mean that's an equivalent counterfactual that this means that in similar circumstances, the confidence variable resulting in no ties forming.
No, this is a great question. So it can work both ways. So since this is a change statistic, right now we're focusing on a counterfactual where the tie count decreases. But envision a scenario where this is actually a negative relationship, and so people are avoiding somebody for a particular reason. We eliminate that treatment condition, and all of a sudden the ties here actually increase. And so this problem about is social isolation being produced because maybe people are avoiding people with a particular type of stigma? Totally possible here. Yeah, great question. Okay, so if we're good, then this is kind of the other workhorse component of the MEMS, and I don't really expect you to read through all the pseudocode. But the basic idea here is that since we have a formal property to this target quantity, we can actually plug it into a very generic parametric estimation algorithm that's actually reasonably widely used in system engineering. And the idea behind this algorithm is you can take the uncertainty from an empirical model based on the covariance matrix you actually get, the standard errors you actually get, the coefficients you actually get, and use those uncertainty values to simulate a range of potential outcomes for the network. Now, based on that, what you're actually able to do is take this target quantity that is not a direct expression of the model we're observing and get a standard error confidence interval and p-values and everything associated with it in order to do null hypothesis testing on a micro-macro relationship. So the second part, I don't want to dwell too much on the inner workings of the algorithm because it's not super important for applications. But the second part is really how you're able to start conducting hypothesis testing on the MEMS. So even though the outcome we're interested in, degree centrality, betweenness centrality, segregation, transitivity, are not directly modeled with your model specification, you can estimate and test the effect of anything you stick in the model on those outcomes. Okay? So let's see how it works. We're going to switch over to R. And I circulated some R code. Now, for the purposes of this, I included, as I always do, way too much. But I'm hoping it's useful. We're not going to go through all of it, but there's a ton of supplementary resources here for different ways you could use the MEMS to test some of this stuff that I'll be talking about a little later. So to start, we're going to load in the NetMediate package. And the NetMediate package is really the workhorse package that does everything related to the MEMS. And even though the user-side interface is pretty streamlined, there's a lot of functionality on the back end. And so it supports all types of models, from standard regressions to relational event models, ergms, different types of ergms, parametric, non-parametric ergms, stochastic actor-oriented models. And it'll do it all for you. And I wrote way too extensive help pages, so please use them. OK. The other two things that we'll be loading in to work with the NetMediate package are StatNet and iGraph. These are necessary for basic interactions with the network data that we're using that are kind of underlying the MEMS framework. And then finally, we'll load in our Sienna. Even though we probably won't get to the Sienna models today, we'll be borrowing that data because it has stuff on smoking behavior. And well, that's about as in-depth as I get with health. OK. So what we're going to be looking at is on line 19, we're creating a network panel data set. So this is a list. We're creating a list of two network objects from these two matrices, adjacency matrices, that are imported by our Sienna. And these are two panel observations of the Teenage Lifestyle and Health Study, which followed, I believe, Scottish high school women over about a year of activity, and their friendship relationships and how it related to their smoking and drinking behavior. And so we'll assign two variables also from the R Sienna package, which is simply the smoking behavior at wave 1 and the smoking behavior at wave 2. So if we take a quick peek at the data, this is just the second wave of data right here. You'll see we have 50 nodes, so 50 women, a directed network, 116 edges, and we get their smoking behavior as well. So this is ordinally measured. And since we just went through visualization, here's the obligatory visual. We get some clustering, we get some people in the middle, we get some isolates. OK. So in order to use the MEMS, we first have to fit a generative model for the data. And so on lines 33 through 39, we're just going to run this. And this is going to fit a dynamic exponential random graph model. So this is a temporal exponential random graph model. It has the same functional form, approximately, as the ergom that Jim was talking about earlier today. This little wrapper here, form, indicates that we're only modeling the formation of new ties. We're not modeling whether ties persist across waves or whether people dissolve those ties. We have the edges term, which Jim touched on earlier. This is our intercept for the model. We also have sender and receiver effects. So node I-cove is modeling whether girls who smoke receive more ties, and node O-cove is modeling whether girls who smoke send more ties. The abs-diff term is a measure of smoking similarity, and so it increases in value as two girls' smoking behaviors are further and further apart. So it obtains the highest value for people who smoke regularly and people who don't smoke at all. And finally, this GWESP term is just that nonlinear triadic closure term that Jim was talking about earlier. It essentially is modeling the probability that two girls will become friends if they share a mutual friend with diminishing returns as the number of shared friends increases. So we can summarize the model output. And again, what we're looking at here are our coefficients determining whether two girls are more or less likely to be connected. And so what we're observing for the node I-cove term is a non-significant incoming smoking effect. P-value is kind of marginal, suggesting that we're not seeing any evidence that girls who smoke receive more ties. The O-cove effect is also null, suggesting that girls who smoke do not tend to send more ties. The absolute difference in smoking behavior is negative, suggesting that as two girls' smoking behavior becomes more similar, they're more likely to become friends. So homophily on smoking. And we see a positive triadic closure effect, suggesting that if two girls share a mutual friend, they're more likely to be friends. So again, at this point, what we've done is model the probability that two girls will become friends. What we have not modeled is what's causing all of this local clustering in the network we're observing. So now we're going to get in the MEMS framework to try to decompose which of these coefficients is actually driving up the transitivity in the network we observe. So line 58 will pull up the MEMS help page with, again, way too much detail, but also a lot of options. And on line 71 through 76, this is where we'll actually do the estimation. So there's a few key parameters we need to provide. The first is the model itself we'll be using to generate the estimates. So this is TLS model, which is just the model we just fit, the ergom, the tergom that we just estimated and interpreted. The second is the microprocess. So this is the model term that we are trying to explore, or that micro-level selection process that we want to hypothesis test. So we can do this for every single unique term in the ergom if we want to. And right now what we're focusing on here is form absolute diff smoking. So we are modeling the effect of homophily on smoking on transitivity at the aggregate. And note that this language, the notation here, has to match exactly the model output. And so we're expressing it in this exact form to match the names of the coefficients in the tergom output. The third key parameter is the macro function. This is where you declare your dependent variable. So right now we're using gtrans, which is just a statnet command for calculating the global transitivity of a network. Now below, we're going to get to more complicated user functions. You can write your own function. Anything you can define on a network, you can treat as the dependent variable. So it's one of the major utilities of the package is the ability to write your own user functions for any type of outcome you want. But it'll also take these prepackaged functions like transitivity and degree centrality. We have to declare the object type. This is simply telling netmediate whether you are getting your macro function from statnet or from igraph. If you're calling from igraph, igraph object. Calling from statnet, network object. And the last parameter, nsim, is the number of simulations you use to calculate your standard errors. Now, the default is 500. You usually want at least 500 or 1,000 for reporting purposes, but for workshop purposes, you want things to run a little quickly. So we've pushed it down to 100 here just to speed things up, but that's not publication standard. OK, so now we've got our estimate. So again, this is the effect of selection on smoking behavior on clustering at the aggregate level. We're getting a MEMS of 0.032, but it's got a p-value of 0.15 and a standard error of 0.09. I think that's, no, standard error of 0.04. And so what this is suggesting is something that's actually a little unintuitive. One of the things that we often say drives clustering and behavior is homophily on certain attributes. And this is not to say that process is not happening, but in this particular case, the smoking homophily, when working in isolation, does not appear to be driving up the amount of transitivity we're observing at the global level, at least not by substantial amounts. So the interpretation we can arrive at, if we're seeking to interpret this quantity, is that smoking homophily at the micro level is increasing the observed amount of global transitivity by about 0.03. Now, is that a lot or a little? We can look at that by calculating the proportion of the observed transitivity that is actually explained by this effect. So here the observed proportion is about 0.09, suggesting that about 9% of the global transitivity we observe is explained by smoking homophily, but that effect is not statistically significant. Make sense? Should we pause for questions here or keep going into more examples? Lynn?
Would you use this example to illustrate your general point about the fact that you aren't really looking at the effect of a treatment, but are looking at the ability of something to explain something in your specific data?
Yes. Yes, exactly, right. So, and this is, I think this is a fantastic point. And so what Lynn's pointing out here, rightly so, is we have a lot of work showing that homophily does increase clustering in networks, right? But in this particular case, and this particular type of homophily, we're not seeing that relationship being substantial. And so this is why that case-specific logic is really, really important. And so that's not to say that it's not telling us something important, right? One argument out there about homophily is maybe it's multiple types working in combination. And actually, I'm going to get to how we can test that momentarily. But what we are seeing is that in this particular data set, with this particular level of clustering and this particular level of smoking homophily, this parameter itself isn't doing the job. Other questions? Tom?
As far as what the macro function looks like, here we're looking at a type of homophily and then an effect of a property. Is there a way to have like an attribute dependent, like for instance, if you want to know the effect of transitivity on smoking homophily, right? That like can you set it so that
Oh, scroll down, dude.
Okay.
No, no, we've got examples further down here. Yeah. No, this is a fantastic question. So right now, one of the utilities of the basic functionalities, if you don't want to change anything about the default specifications of an argument coming from StatNet or iGraph, you don't have to. But if you do, you have a lot of flexibility in the user functions you specify. And there's actually some workhorse functions in the MEMS package that'll deal specifically with coevolution, stochastic actor-oriented models. If you're doing this kind of decomposition selection and influence framework, there's an under-the-hood function that'll do all of that for you in NetMediate. But yes, we'll get back to this point about user functions momentarily. Yes, Twa. Great question. Yes, yes, and yes. So by default, when we're working with Turgum objects, NetMediate will use the second wave. That's intended to make it comparable with RCNA, which is they use the terminal wave for goodness of fit checking, and simulations within the stochastic actor-oriented model framework. But you have a lot of flexibility about this. And so actually, if you're using other types of models, so a particular way of thinking about some specifications of a Turgum is as if you are not including specific parameters, it becomes a dynamic GLM. And if you're using a type of longitudinal model that has a time indicator, the MEMS package actually lets you specify a time interval. And so you can specifically say, I want to measure the effect after pooling the third and fourth waves of data. Or I want to measure the effect separately on the third and fourth waves and then aggregate the effect. Or I only want to look at the fourth wave. So you have a lot of flexibility here. And this becomes especially useful when you're doing relational event sequences. Because in a relational event model, you're modeling every single interaction independently. And so you actually have to define an aggregation window if you want an aggregate property of the network to be the dependent variable. So if you say nothing, NetMediate will make assumptions and do it for you. But you can tell it to stop and specify that however you want. The other question was about predicting to new networks. You can. And in fact, NetMediate includes this interval parameter. And what this interval parameter is intended to do is change the weights you assign to the potential outcome values. And so one thing you can actually do is if you say, I'm actually not interested in testing on the observed data, I'm interested in exploring in a simulation framework, which is more what Carter's going to be talking about. You can pump these values up to something that just reflects nothing about what you're observing. Like if the interval is set here to 2, it'll take your treatment value and multiply it by 2, and then compare it to the lower end, which you can also set to like 1 or 1.5 or something like that. And what this will let you do is if you get an unintuitive result, like why is homophily not explaining transitivity, you can change the question and say how much would the homophily effect need to increase by for it to explain transitivity. And all of a sudden, you can actually pump this up over and over and over to uncover tipping points that you might not expect from the data. So when you do that, you lose that statistical interpretation, but you get back into the simulation framework, which might be interesting, depending on what you're thinking through. Yeah. OK, I want to get to some other stuff, because a lot of these utilities are built in here. And I want to talk about some other statistical things we can do here once we get this under our feet. So a second way of thinking about these micro-macro quantities is there's this idea out there that on its own triadic closure probably, if we're looking at segregation as the outcome, on its own triadic closure probably doesn't drive up segregation. But if we introduce it into a network that already has some level of homophily, it can really exacerbate that. And so what this is actually doing is it's a hypothesis on 2 parameters operating at the same time. And so we can take the MEMS framework, and we can actually do this exact same thing by examining the joint effects of 2 coefficients at once. And so if we run this code, what we're going to get is rather than looking at the effect of smoking homophily independently, holding triadic closure constant, we'll get the effect of smoking homophily and triadic closure operating at the same time on the observed level of transitivity. And so here, now we're actually starting to see things that align a little bit more with what we might expect. Personally, the fact that we're actually parameterizing the effect of triadic closure and the p-value is still 0.05 is a little surprising to me. I would expect this effect to be a lot stronger. But in this particular case, what we're seeing is that even when these smoking homophily and triadic closure are operating in combination, they jointly can explain about 16% of the global transitivity we observe in the network, holding everything else constant. People with me?
With the proportion of change, there it's 15 and before is 0.09.
Mm-hmm.
Does that mean that the 0.06 is, can you, how to interpret that? That is an additional 0.06 proportion of change because you added.
Yes. Yes, actually, exactly right. So it's an additional 0.06 of change because you added a triadic closure effect. And later, we're going to talk about how you can actually test that change in itself, because it might be meaningful to interpret in the same sense as you might be interested in how much does the effect of race moderate the effect of income on educational attainment or something like that. Right? Yeah, it's great. So one of the things that's really key about the MEMS is that in order to do this decomposition and talk about it as an effect on the observed data, you would ideally do a good job of explaining the observed data. And so if we have a model that's actually not plausible for the outcome we're trying to measure, then we might be a little more suspicious of the estimates we get. And so in the MEMS framework, we can do this type of litmus testing in the same way that you might do with general model fitting in ERGM. And so all I've done here on line 103 is rerun this command that we had before. I've set the silent option to true, so our global environment or console doesn't stay as cluttered. And I set full output to true. Now what full output, setting it to true, what it's going to do is actually return every single simulation sample that was generated by the estimation algorithm. And so if you're interested in things like changing the estimate from the average across samples to the median, or simply looking at the sampling distribution, you can do that by setting full output true. So looking at the names of the data that we just generated, what we get are the summary statistics, which we already evaluated, the output data, which is the individual samples for each potential outcome we were looking at, the MEMS samples, which are the individual differences in potential outcomes, and then the e-value data, which we'll talk about later as a sensitivity test. So based on that, what I'm doing on line 119 and through line 130 is a simple gut check of how well the model-generated samples are actually aligning with the observed transitivity. And so this figure's a little small, but here what we have, this is the counterfactual when we eliminate the effect of smoking homophily and triadic closure at once. This is the model-generated value when everything is operating, and this is the observed level of transitivity. And so what this is telling us is that our observed level of transitivity is about 0.37. Our model-based estimates look to be about 0.33, maybe. So we're underestimating transitivity slightly in our model, which suggests we probably could do a better job. And that's not super surprising because this is a very, very, very sparse model. But at the same time, we're not off by a huge margin. It's not like we're totally whiffing it. OK. So now what I want to talk about briefly is these more complicated user-based functions. And so what we've done so far is we've relied on a function that's exported directly from StatNet. But like Tom was saying, we might be interested in how much is transitivity contributing to smoking homophily, not how much is smoking homophily contributing to transitivity. And so the way we can grapple with this is by writing our own user function. And so what NetMediate does under the hood is any attribute you include in a model, it will internally interface with. And so you can provide as an input condition any function that takes a network or an iGraph object as an input and then outputs a numeric value. As long as you do that, NetMediate will work. And that means you can write a whole wide range of user functions to interface with the networks and treat as dependent variables in this framework. And so here, all we're doing is taking writing a user function that essentially is just calculating the amount of network autocorrelation on smoking in the first neighborhood. So this is a very common measure of network segregation according to specific types of behaviors. It's the one that's frequently used in the RCNA framework. And so all we're doing here on line 157 is getting that smoking attribute, which NetMediate knows how to work with because we already have it in the model, and then calculating the first order network autocorrelation on it. So we can write that function. And now on line 163, all we're doing is changing our dependent variable. So now we're looking at how the effect of smoking homophily contributes to, at the micro level, contributes to smoking homophily at the macro level. And here we are still seeing kind of, this one's a little harder to interpret. I'm not sure how much of it is because we have a small number of simulations that the p-values are a little larger than we would expect. But the effect size seems to be large, but there's so much variance around that effect size that it still is too uncertain to reach conventional thresholds of statistical significance. So here we get an interpretation of smoking homophily at the micro level contributes or can explain about 50% of the smoking homophily we observe at the macro level in the data. But that effect doesn't reach statistical significance thresholds. OK? And we can do that same thing with triadic effects. And here we're seeing more of the same, but the effect size is weaker. Questions? It does, but this is kind of an interesting thing because the place that actually matters is in the certainty you get in your model estimates. So it's really any uncertainty we're getting in the MEMS estimates is a function of the uncertainty we're getting in the model-based estimates. And so it's not so much that the number of observations are mattering directly for what the algorithm is doing, but they are mattering for the amount of uncertainty we're getting when we're doing our simulations based on those model parameters. Yeah. Good question. Other questions? Yep.
Okay, so I'm just gonna caveat this, it sounds so super basic, but your last statement, and I'm just noticing all these
Yeah, you definitely do. Yeah, you can get positive or negative estimates. And so We can have it move in either direction, but one thing that's important to know about the MEMS is the estimates you're getting are partly a function of the distribution of variables and partly a function of the distribution of preferences. And so you can have something like a negative coefficient that we often want to interpret as reducing the probability of people being connected. But if everybody actually has very, very similar levels on that, or very, very small values on that particular value, then when we estimate the MEMS, it might reverse in direction. And so sometimes we can get these unclear pictures because since we're aggregating to the macro level, we are taking into account the entire shape of the distribution. And so sometimes the results can be like, well, why is the MEMS the opposite direction of the coefficient? And that's because it's a feature of the data. So it's a feature, not a flaw. But yes, you can. Yeah, good question. Okay, so we've been through, I've got about 10 minutes left. And what I want to do is talk about some extensions. So far, what we've covered is a lot of things about how to interpret the MEMS, a lot about how to use the MEMS for hypothesis testing, caveats surrounding it. But as a statistical quantity, I mean, most of the things that actually come from the MEMS that I think are particularly useful and novel is that it allows us to do a lot more kind of principled robustness checking and sensitivity analysis than we might be able to do if we only thought about it as a simulation value. And so two caveats that come up when we're estimating the MEMS is we have these usual type of assumptions that go into a regression framework, such as no omitted variables. And so it can be the case that when we have an omitted variable in our model, that the estimate for a particular MEMS is actually biased in some unpredictable direction because the coefficient that we're using to generate the MEMS is biased as well. And so we can test this using a very kind of common sensitivity analysis, which is just the e-value. So this is the work that Lewis has contributed to, which is we can redefine the e-value to work with the MEMS, even though the MEMS is not an explicit function of model-based coefficients. And so for those of you who are unfamiliar with the e-value, essentially what it's telling you is on a rate ratio or risk ratio multiplicative scale, how much larger the effect of an omitted covariate would have to be to eliminate the effect you observe. And so NetMediate spits out e-values whether you want it to or not. And what we get back for this particular run is an e-value of 1.5. And so what that's telling us is if there's an omitted covariate in the model, the MEMS for that covariate would have to be 50% larger than the MEMS we estimated to totally eliminate that effect. So we can use this as a pretty basic way to do sensitivity testing, or as Jim was saying earlier, to throw it back in the econometrician's face or whatever you want to do, as a way of just kind of gut checking what the quality of the estimates we actually are getting. Now the other thing to remember with the e-value, of course, is it's a hypothetical quantity. So you can have a true estimate that has a really, really small e-value. And that doesn't actually mean it's a bad estimate. It can be right. However, it can still be useful in terms of thinking through the robustness. A second key assumption is that the functional form of the model is correct. So far, by assumption, we've been saying A is a function of a chosen model. And previously, I said it was tergum. Now, if we're thinking back to the selection and influence debate that Jim was talking about earlier, we know that the autocorrelation we're observing in a network could be because smokers pick other smokers as friends because they can smoke together and it's a nice thing to do during downtime. Or it could be you have smokers as friends, and that's driving up your own smoking behavior. So the classic way of handling this problem is with a stochastic actor-oriented model that can disentangle selection and influence. However, if any of you are enmeshed in the longitudinal networks data literature these days, you know there's kind of an active debate about the adequacy of SALIM as opposed to tergum and the assumptions they make, even writ of these types of behavioral selection and influence questions that we have. And so in terms of thinking through the MEMS, there's actually a very simple sensitivity test, which is you're modeling the exact same outcome, estimated on the exact same scale, which is the scale of the outcome you observe. And so a very simple way to test the sensitivity to model selection is to just do it both ways, and then treat the difference in model-based estimates as the target quantity. And so if you do this in the MEMS framework, this is the difference in a tergum-based estimate of the effect of smoking selection at the micro level on smoking homophily at the macro level, as compared to a coevolution Siena model that disentangles peer influence and smoking behavior, peer influence and peer selection. God. And what we see is there is a difference in those estimates, but the difference isn't so massive it's fundamentally changing our conclusions about the significance. The effect size, it does differ a little. How much faith you put in it is a question. But this explicit test of the difference, the sensitivity to model selection, is not itself statistically significant. And so what this is telling us is, at the very least, we're not able to refute the null hypothesis that one model is telling us something fundamentally different about the selection dynamic, even though we know one model handles selection and peer influence much more explicitly. OK. I'm going to go quickly here. We already talked about some of this, but there's kind of a subtle distinction here that I want to draw out when we're talking about moderation and mediation. So another way we can think about generative dynamics is interactions between different types of variables. Now, because we're working with network data, we can think about interactions as working in one of two ways. One is what I call a right-hand interaction, and this is the exact type of interaction that you're usually thinking about, which is it is the interaction between two variables. You include it as an interaction term, and you get a product coefficient. The second type of interaction is unique to the MEMS, or micro-macro analysis, and it's something that we actually talked about earlier, which is it might not be that actors are pursuing triadic structures with shared attributes more than triadic structures without shared attributes. It might just be the case that triadic closure is occurring in the presence of homophily. So let me write this out on the board, assuming these things are working. And they are. So a right-hand interaction, this is a triadic substructure, 3 nodes with the same characteristic. This is a triadic substructure, 2 nodes of the same characteristic and 1 node without. A right-hand interaction is telling you that this substructure is more preferable than this one. Actors pursue this particular triadic configuration because they want to be in triads where everybody is the same. A left-hand interaction is saying it doesn't matter. There's no difference in preference here. However, in the observed data, triads tend to occur in these structures more. And in this case, either of these processes could actually contribute to greater segregation at the aggregate level. It could be just a feature of the data that triadic structures are emerging within homogeneous groups, or it could be that actors are pursuing those structures. And that's the difference between the right and the left-hand interaction. A right-hand interaction is focusing on the preference. The left-hand interaction is just the data. So we test them in slightly different ways. The right-hand interactions are actually tested in a very simple way, which is you're going to get an interaction coefficient, and you're going to test the MEMS on that coefficient. And that is the MEMS for your right-hand interaction. The left-hand interaction, we have to go through the process that we had touched on earlier, which is a 3-stage process where first, you want to know, is triadic closure only contributing to segregation in the presence of some level of homophily? To do that, you first estimate a single parameter test on triadic closure. And this is the same one we got before, non-significant. Then you do a joint parameter test with homophily added in. So this is accounting for what is the effect of triadic closure in the presence of homophily. Now the problem is this contribution, this MEMS we estimate, partly contains the value of triadic closure because of homophily, and partly contains the effect of homophily itself. And this is where the third step comes in. You calculate the difference. And so here, and this goes back to Tua's earlier question, we get a difference of 0.09. And because we can actually get those exact sampling distributions of the estimates, we can get a standard error that's accounting for the covariance of those two effects as well. And so this 0.09 is telling us that the effect of triadic closure on smoking segregation increases by 0.09 when we add smoking homophily into the mix. Make sense? Last thing, I swear. The last thing that we can use the MEMS for, which is really only possible because we're thinking of it as a statistical quantity, is teasing out indirect pathways. And so far what we've been talking about in terms of preference and segregation and triadic closure has been about the effects kind of amplifying one another. But it could also be that the effects are feeding into one another. We might only have access to triadic substructures because they're being generated by individuals' levels of pursuing members of the same group. And so in this case, what we're actually working in is a very common framework of mediation analysis, where we have a macro level outcome, smoking segregation or smoking homophily at the aggregate. We have a micro level input, which is smoking homophily at the micro level or choice-based preferences for people who have similar smoking behavior. And then we have an intervening variable at the micro level, which is the number of triadic substructures created because people who smoke tend to befriend other smokers, and that creates small local groups. We can test this in a pretty straightforward way by estimating the MEMS from two models and then taking the difference. And so in this case, we're introducing a new mediating variable with a coefficient tau. And that mediating variable is a stand-in for triadic closure. We estimate a model without that coefficient, and then we compare the difference in the MEMS between those two models. And when we do so, we get three quantities back. The first is the total effect, which is the effect of smoking homophily on smoking segregation, both directly and indirectly by creating triadic structures. We get the direct effect, which we're getting from our second model, and that's the effect of smoking homophily on smoking segregation because of its direct contributions. And then we also get this indirect pathway. How much does smoking homophily contribute to smoking segregation because it's creating opportunities for social closure? And again, we can test each of these pathways individually in a pretty straightforward decomposition. And so here in this particular output, we get the partial MEMS, which is the direct effect. We get the full MEMS, which is the total effect. And then we get the difference or the change, and that's the indirect effect. And so here we're not finding evidence, I don't think, of any particular pathway being driving smoking segregation. I'm right on time, so I'm stopping here.
Since we are butting up against coffee here,
it really depends on the substantive reasoning. The plausibility of these counterfactuals, and maybe I was ineffective at getting at this, really depends on the type of network you're looking at. And I think sometimes it depends on the type of heterogeneity that's embedded in that network. And so if we're looking at something like the networks I look at, trade networks on illegal marketplaces or online marketplaces, this counterfactual, I think, is actually plausible for some conditions. Like if I'm going into the market, and this is what it looks like when I'm buying heroin, and now I'm eliminating the availability of heroin. I'm a heroin user. Why am I on the market? I think that's reasonable. However, if I'm modeling something like students entering a new college setting, and what I've previously seen is that they enter through shared affiliates or shared preferences because they don't know anybody, they link to the people who have shared interests. And now I eliminate shared interests. Are we saying they make fewer friends, or are we saying they shift their standards? That's where the counterfactual becomes a little more dubious and harder to interpret. And so in those settings, that's where I'm not yet ready to make a claim. But the follow-up I want to make to this is when I'm saying we can't interpret the counterfactual, what I mean is I have not shown it. So I do have formal proofs available about the types of conditions that you can interpret the MEMS for. And they're weaker criterion than ones that allow you to interpret the counterfactual. So I have not shown that the counterfactual is uninterpretable, but I have shown that the factual is interpretable when we compare to the counterfactual. And so this is to say that a lot of the caution I'm ushering is not to say it's impossible, but because I don't know. So two things can be true. Yeah.
Well, so I'd like to add to your defense.
Thank you.
So I think, forgive me, I know no sociology, but I'm wearing my mathematician hat. I think what you're actually stating is simply that from the case that you're observing, when you use this particular strategy to eliminate the particular mechanism for emergence of the particular instance, what you might have been doing is what, in my own language, I would say, is removing that particular approximate mechanism for generating that emergence, and that there's a baked-in assumption that that is the reason in what you are seeing that will therefore disappear. It may not disappear for that reason, either mechanistically or statistically in a causal forward direction, and that's what you meant also by the left-handed direction.
Yes.
And so it's not that this is uninterpretable, it's that you're making an underlying very strong assumption
Yep.
that there is a unique causal left-handed mechanism.
Yeah.
And so that's still very interpretable. It's just that you need to explicitly say, like, okay, my interpretation is the left-handed assumption is true.
Yes. No, this is probably a more precise way of me than I would say it, right? But I think this is exactly what I'm trying to get at in terms of thinking through the substantive process that we're looking at when we're generating the counterfactual. Because one particular way of thinking about it is if we eliminate this particular mechanism, we're making the assumption, again, all else constant, which is frequently problematic in some settings, but not all, right? And so that's why we have to be explicit about that assumption, because there's one argument is essentially, this is the counterfactual assuming a fixed data generating process. But in the real world, if we eliminate a mechanism, the data generating process changes. And so how do we estimate?
I do think it's stronger than that. I will argue later.
Sounds good.
I think I can make it work stronger.
Thank you. I look forward to it.
Now, let's get some coffee